In this podcast, we're going to look at the properties of gases, including kinetic molecular theory, various gas laws, molar volume, density, and stoichiometry related to gases. So first of all, as we know that gases expand to fill the volume of container in which they are present, because their particles are very far apart and they have almost no interaction between their particles, or intermolecular forces of attraction are totally absent. So if you could look inside a gas sample, what you'll see is mostly empty space interspersed with few particles. For example, in a sample of air, only 0.1% of the total volume actually consists of matter. Rest of it is just empty space. So why do gases have the properties that they do? Why are they expandable? Why do they take on the volume of a container? Why are they so compressible? All of this is explained by a theory called as kinetic molecular theory, or KMT. KMT provides a particulate level theoretical explanation for the practical behavior of gases. There are some postulates or assumptions that KMT makes to explain the behavior of gases, and these assumptions are that gas consists of particles that are very, very small. They are tiny, that they are point masses. There is no volume occupied, they just have a mass. So the assumption that KMT makes for gases is the volume of particles is negligible or is close to zero. The second postulate of KMT is gas particles have a specific type of movement which is called as Brownian movement. They keep traveling linearly in a straight line till either the gas particles hit other particle or they hit the wall of container. And these collisions with each other are elastic collision, meaning there's no energy loss as a result of these collisions. The next postulate is that gas particles do not experience intermolecular forces. The next postulate is gas pressure is caused when the gas particles collide with the wall of the container. Note, gas pressure is caused by gas particles colliding with the wall of container, not with each other. And the average kinetic energy is directly proportional to the absolute temperature of the gas. If two gases are at the same temperature, their average kinetic energies would be the same. So these are five main postulates of kinetic molecular theory, which explains the behavior of gases. And at the particulate level, if you had to draw gases as particles, let's draw and see some. So here are five different gas particles. KMT says that the intermolecular forces of attraction between them are negligible. So gas particles move independently of each other. When the gas particles collide with the wall of container, they exert a force, and this force per unit area is called as pressure. So the two ways of altering the gas pressure could be either you change number of collisions, hence you change the force, and you can change number of collisions by speeding up the particles or by decreasing the volume of container. So force per unit area increases. The other way of changing gas pressure is each of these collisions exerts more force. Then the force per unit area will increase and the pressure will increase. So these are some ways that gas pressure can be changed by changing volume or changing temperature, and obviously changing number of gas moles. Pressure is very important to understand the amount of gas. Just like for solutions, you express their concentration by molarity or mass percent, which tells you how much of solute is dissolved in solution. Similarly, a pressure is an indicator of how much gas you have in a container. Now, atmospheric pressure is the pressure that the layer of air exerts on the surface of Earth or upon all surfaces, and this pressure is given by force per unit area. And these are few conversions between different pressure terms. 1 atm is 760 millimeters of mercury, which is equal to 760 torrs, 101.3 kilopascal, and 14.7 psi, or pound per square inch. I recommend that you memorize the interconversion of these different pressure units. Moving on to how we measure pressure. To measure atmospheric pressure, we use an equipment which is called a barometer. A barometer balances the atmospheric pressure by the column of a mercury, and the height of this column indicates the atmospheric pressure. And if you wanted to calculate the pressure, the formula is H times D times G, where H is the height of the mercury column, D is the density of mercury, and G is gravitational pull, 9.8 meters per second squared. The gas pressure can be measured by manometers. Manometers can be open-end or close-end. The close-end manometer has vacuum on the side where mercury is present. So gas pressure is measured in absolute terms. And here, pressure of gas in a closed manometer is given by the height of the column. So if you wanted it in ATM, you'll do H times D times G, or just the height. If you write it as millimeters mercury, that is the gas pressure. However, in an open tube manometer, gas pressure is given against atmospheric pressure. So if the side of the gas is lower than the atmospheric pressure side, that means the gas pressure is higher. By how much? By the difference in their height. So in this case, gas pressure is equal to atmospheric pressure plus the pressure due to the height of mercury column. And in this case, this is again an open-end manometer where the gas pressure is lower than the atmospheric pressure, and you know it because the arm in which gas is exerting the pressure has a higher level than the atmospheric pressure, and the gas pressure is given by atmospheric pressure minus the pressure due to this height difference of mercury. Now there are various gas laws. Please remember that all of these were experimental observations that scientists observed about the nature of gases in their laboratory, and these are explained by kinetic molecular theory. Remember, all of the gas laws are only applicable when the temperature is in Kelvin. So even if a problem gives you temperatures in degrees Celsius and asks you to write it in degrees Celsius in your answer, you still have to convert it to Kelvin. There is Boyle's law, which gives you pressure volume relationship, and it says that if for the same quantity of gas at the same temperature, volume and pressure are inversely proportional to each other, or PV is a constant. There is Charles' law between volume and absolute temperature, which says volume and absolute temperature's ratio is a constant. So if you plot a graph between V, volume of a gas, and the absolute temperature, you get a linear graph. If you extrapolate that graph, then at zero volume, the temperature is called absolute zero. And because there's no such thing as negative volume, absolute zero is the minimum possible temperature for a substance. And that was Charles' law. The next law is Gay-Lussac's law. And Gay-Lussac's law says that pressure and temperature ratio is constant if you keep for the same quantity of gas and you keep the volume the same. So P1 over T1 is equal to P2 over T2 is Gay-Lussac's law. Avogadro's law says that equal volume of gases at the same temperature and pressure have the same number of moles. So if you plot a graph between volume and number of moles of gas, you'll get a linear graph. Avogadro's law also talks about concept of molar volume, which says 1 mole of any gas at STP, or standard temperature and pressure, which is 1 atmosphere and 25 degrees, and 0 degrees Celsius, not 25 guys, that's RTP, and 0 degrees Celsius occupies 22.4 liters of a gas, of the volume. So molar volume is 22.4 liter for 1 mole of any gas at STP. If you combine all the laws except for Avogadro's law, you get combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. An ideal gas law, or PubNert, is when you combine all the gas laws, where P is pressure, V is volume of gas, N is mole, R is gas constant, which is 0.0821 liter atmosphere per Kelvin mole, and T is temperature in Kelvin. Guys, remember, all the gas stoichiometry problem either will be based on molar volume concept if the gas is at STP, or you will be using ideal gas law or PubNert equation. There are three forms of PubNert equation. One is the PV is equal to nRT. Second is written in density, or D is PM over RT. And the third way is written in terms of molar mass to calculate molar mass of an unknown gas. Moving on to Dalton's law of partial pressure. So what happens if you take a bunch of gases and mix them together? Individual gases' pressure in a mixture of gases is called partial pressure. Dalton's law of partial pressure says that the total pressure of a mixture of gas is equal to sum of individual pressures of gas. So P total is PA plus PB plus PC and so on. And because for Avogadro's law, pressure is directly proportional to number of moles of a gas, you can also write N total is equal to Na plus Nb plus Nc and so on. The application of Dalton's law is when we make a gas in the laboratory and collect it over water. What happens as you bubble the gas? Let's say you're making hydrogen gas by reaction of zinc and hydrochloric acid in a test tube. So I have a test tube in which I put some zinc metal and added hydrochloric acid to it. As a result of it, what I'll start getting is hydrogen gas, and then I take this hydrogen gas and I let it bubble through the water. I can collect any gas this way that's not very soluble in water, and initially the water is filled all the way in this inverted test tube or a bottle. But as you start collecting the gas here, the level of water keeps going down. So even though you cannot see the gas, you can see the gas collecting as the level of water starts going down. This is called collection of gas over water. So you're intending to collect only gas, but because you're collecting gas over water, what else gets collected in there are water molecules. And when the level of water inside and outside the container are the same, that means at that time the atmospheric pressure is equal to the pressure of gas plus the pressure of water vapor, because that's snuck in there. So if you want the pressure of gas, you've got to take away the pressure of water from atmospheric pressure, and this pressure of water is called vapor pressure. It depends on temperature, and there is a table looking at which you can figure out how much is the water vapor pressure. So if you subtract the water vapor pressure from the total or the atmospheric pressure, you get the pressure of gas. So that is about collecting gas over water. Now this is a problem with application of PubNert equation. Why don't you attempt this problem, pause here, attempt the problem, and then check your answer with the solved out problem. And these are the answers. Mole fraction, or X, is ratio of moles of one component over total number of moles. And another modified way of writing this is pressure of gas A is equal to mole fraction of gas A multiplied by total pressure. And this equation is also very useful in figuring out how much would the pressure be of one component in a mixture of gases if you know the total pressure. It's only a logical equation because you know that pressure of a gas is directly proportional to number of moles. The higher the number of moles, the greater will be the pressure. So if from total pressure you want to figure out how much is the pressure exerted by one component or one gas, then you have to multiply the total pressure by its mole fraction. Average kinetic energy of gases. So kinetic energy, as you know, is half mv squared. In case of gas, for average energy, for average velocity, we use root mean square velocity, RMS. This is nothing but the average velocity for gases. So kinetic energy is half m u RMS squared. Here you have to remember, because you're getting your answer in joules, the mass must be in kilograms. And then when this is meters per second, that's equal to joules. So average kinetic energy of gases can be calculated using this formula. And if you recall KMT, guys, average kinetic energy of gases is directly proportional to the absolute temperature. So if there are two gas samples at the same temperature, then their average kinetic energy will be the same. Now listen carefully. Even though their average kinetic energy is the same, it doesn't mean that their average velocities will be the same. For here, let's consider two gases. One gas with larger gas particles and one gas with smaller gas particles. They are both at 20 degrees Celsius. Let's call this sample A, let's call this sample B. Because they're at the same temperature, their average kinetic energy is the same. If average kinetic energy is the same and one of them is a smaller particle, then the smaller particles must be traveling at a higher average speed than the larger particles to get the same kinetic energy. Now let's look at a couple of animations to bring this point home. The first animation actually talks about states of matter, and let's just look over it to reinforce some of the property of gases that we already know. This is neon sample, and so guys, just a quick review. What kind of intermolecular forces will be present in solid neon? If you answered London dispersion forces, you are right. And as you apply the heat is used to overcome the intermolecular forces or London dispersion forces. And with time, you can see that the solid particles are dissolving and making liquid particles, and eventually it's turning into gas. And you can see that in the gas, the particles are farther apart, very little intermolecular force of attraction. They are colliding with each other and also with the wall of container, and these collisions with the wall of container cause pressure. Now if we reset it, and let's choose oxygen. Just close that got opened by mistake. And let's come back over here. And let's apply heat to this oxygen sample. Between oxygen molecules, again, there will be only London dispersion forces. And you note, as you apply the heat, the oxygen molecules separate out. Those intermolecular forces of attraction are broken. However, oxygen molecule does not break into oxygen atoms, right? It stays together. And let's reset it and now look at water molecules. As you apply the heat, the water molecule changes to liquid, which is so much more dense than the solid, guys. Water is one of those substances where the solid is less dense than the liquid. And then you see that it's turning to gas phase. Now let's look at another animation which talks about some of the properties of gases that we just talked about. Let's first start with heavy species, larger particles. And as we pump the particles in there, see now the gas pressure is generated as these particles start colliding with the wall of container. What do you predict will happen if we heat up this sample? Yes, you're right. With heat, the pressure increases. And can you tell me the reason of this pressure increase? The reason for this pressure increase is because now, as you added more heat, the average kinetic energy of particles increased. With that, each collision's force increased and number of collisions increased as well. And that resulted in higher force per unit area. Now guys, let's add a light species to it. And as we add light species to it, note that the pressure further increases because now there are more particles. Guys, one thing to clarify, did the total volume of the container change? No. So what's a container of red particles? Same as a container of volume. What's the volume of the blue particles? Same as the container itself. And if we add the heat, both particles will start moving faster and the pressure will increase. Now guys, let's look at some of the average speeds. What do you predict? At the same temperature, do you think the blue and the red particles are moving at the same average speed? No. The smaller or the red particles are moving faster. Let's do species information. You can see here that the average speed of the heavy particles is 760, 70, somewhere there, and the light particles are traveling much faster. And that was the point I wanted to show you. Even though they have the same average kinetic energy at same temperature, their average velocity may not be the same, will not be the same if their masses are different. This next graph here is called as Maxwell-Boltzmann distribution graph. On this graph, on the y-axis, you have the number of particles, and on the x-axis, you have a certain speed. Let's put some imaginary numbers here, 10, 20, 30, 40. So let's say this is 25 degrees Celsius for oxygen gas. And if we want to know how many particles have the speed of 20 or higher, it is the shaded area under the graph, only these many particles. How many particles have speed of 10 or higher? There are many more particles, right? Now, if we increase the temperature, then what happens is curve shifts to right. So the total area under the graph is the same in both cases because your number of particles are the same in both cases. But now if you want to see with increase in temperature, let's say this 35 degrees Celsius, so many more particles now have the speed of 30 or higher. So this type of distribution is called as Maxwell-Boltzmann distribution. And with increase in temperature, the curve or the graph shifts to right. All right, now let's look at some of this information. So this is oxygen at 273. Now, if you compare it to the graph of oxygen at 1000, you'll see that the graph is shifted to right because with increase in temperature, you'll have more higher kinetic energy particles. So graph is shifted to right. And can you predict what would hydrogen at 273 look like? You are right. It will be shifted to right as compared to oxygen at 273 because hydrogen is a smaller gas. So its particles will be moving faster at the same temperature because the average kinetic energy is the same. So that's Maxwell distribution graph. Moving on to effusion and diffusion. Effusion refers to escape of gas particles through a small opening from an area of higher to lower concentration. And there is Graham's law of effusion, but effusion and diffusion are used interchangeably. Graham's law of effusion says that the rates of effusion of two gases are inversely proportional to the square root of the molar mass of the two gases. So if you know the nature of the gases or their molar masses, you can figure out the ratio in which they will diffuse out. So a heavier gas will diffuse lesser in the same time as compared to a lighter gas. Now, all of this so far was about ideal gas law, ideal behavior of gases. However, the fact is, guys, that the gases oftentimes don't behave ideally. It's only at the high temperature and low pressure that most gases behave ideally. Rest of the gases behave like real gases. So what is this real behavior like? Real behavior is when gases do not obey all of the laws at all temperature and pressure. And the reason for these deviations are two. One assumption of KMT was that the volume occupied by gas particles is negligible. That is not true. Even though the volume occupied by gas particles is very, very small as compared to overall volume of the gas, it is definitely not zero. As a result of that, the real gases tend to occupy a larger volume than the ideal gas. So a correction factor was introduced to take away a little bit of volume from the real gases to make it more like ideal gas. Similarly, in terms of pressure, because of non-negligible intermolecular forces, because there are some intermolecular forces in real gases. The pressure exerted on the wall is a little bit less for real gases than ideal gases. So a small correction term is added to the pressure of the real gases to make them look more like ideal gas. And this picture illustrates why the pressure of real gases is lesser. So this is one gas particle that is closer to the wall of container, and it's going towards the container's wall to hit it with a certain force. But as it is hitting, if this particle experiences intermolecular pull from the gases adjacent gas particles, then it'll hit the wall with lesser force, which will cause lesser pressure. Hence, in van der Waals equation, which is ideal gas equation modified for real gases, you see that a little correction term is added for pressure, and little from the volume, a little correction term is taken away. In van der Waals equation, P is pressure, N is moles of a gas, V is volume, and R is universal gas constant, T is absolute temperature. A and B are correction term. Correction term A is accounted for the lesser pressure of real gases as compared to ideal gases, and correction term B accounts for lesser volume of real gases as compared to ideal gases. A and B can only be experimentally determined, so these quantities will be given to you. And that is the end of this podcast. Thank you for listening.